Start, sir.
Okay. So this lecture 4, the topic is manifolds. So last time we recalled a few concepts from calculus. So if we needed, we will recall them again or recall more of them. But let us continue now. Of course, our study is motivated by right now by parameterized curve. So if we have a function from an open interval into R, first of all, which is continuously differentiable. If you look at a point C inside the interval, wherein its derivative is not zero, then we know that in a sufficiently small neighborhood U of C, f is strictly monotonically increasing or monotonically decreasing. Equivalently, f will be a one-to-one mapping of U into some interval in U, right? Moreover, the inverse of f defined over fu is also differentiable. So this is all one variable calculus that you know. Slightly generally and slightly weaker is the following. Take a smooth curve J inside Rn, gamma inside Rn. Around each point T0, wherein gamma is regular, it just means that gamma dot of T0 is not zero. The parameter gamma defines an injective map of a sufficiently small open interval around T0. This much we can see, but since this is very important for us, let me outline a proof of this one. And that is the idea involved in this just one-dimensional case is, that's it. That's the whole idea. That will be generalized further. So let us go through this one carefully. T0 is a regular point. It just means that gamma dot of T0, this dot should be outside here, is a non-zero vector in Rn, right? If a vector is not zero, one of its coordinate function pi I of gamma naught must be not zero. At least one of them. Let us say pi 1, the first coordinate, second coordinate, whatever, whichever one. Okay. This just means that d by dt of the composite, pi I composite gamma, it takes first the map gamma and then its ith coordinate, pi I, its derivative at T0 is not zero. So that's by chain rule, the derivative of this is nothing but derivative of pi I, composite derivative of gamma. But derivative of pi I is pi I itself, because pi I is a linear map from R into R. Okay. So from calculus of one variable, we know that just now I have already told you. Now we have a map from J into R, right? This composite map is J into R. So you can apply the earlier observation. You can find an epsilon positive such that inside the interval T0 minus epsilon to T0 plus epsilon, this function, which is gamma followed by the coordinate projection, pi I, ith coordinate of gamma, this is either monotonically increasing or monotonically decreasing. Okay. In particular, it is injective there, right? If the composite of two functions is injective, the first function gamma should be also injective. Okay, restricted to this interval. So this is the gist of the, at least the property of a regular point of a curve, right? So geometrically, it means that there is a small arc wherever you're looking around a point, nightly, right? However, we are not satisfied by just this much of property. When you go to more seriously interesting properties of curves. So far we were good enough. There is, even for many other things, this parameterization as a curve is good enough. Okay. So what I know, it turns out that such a phenomena is also present with vector value functions of several variables also. So that is one particular thing. So at one stage we can go for generalization on one side. On the other hand, it turns out that one needs to assume a little more on the parameterizing function if one wants to achieve certain other desirable geometric properties of the image curve. So this can be achieved in various ways. One easy way is to restrict ourselves to closed intervals. But then we will be excluding very many interesting objects like parabola, hyperbola, and so on, defined all over R. Okay. So if you put too much of restriction, that's out of not good. So based on this kind of considerations, as well as experience in other areas of mathematics, not just the study of curves and surfaces, one brings another concept here, namely the concept of manifolds. So I hope this much is enough for motivation for bringing the manifolds here. Okay, so let me make a formal definition, and then later on study a few properties of manifolds. Whatever calculus we need, we are going to assume. Okay, and also it is related to the present study, namely the curves and surfaces. So let us see how much of this way I can do in one lecture. The remaining I will have to do next week. All right. So many of these things may be new to many of you. So I don't mind any kind of interruptions in between. I will go slowly. Okay. Covering the material is not the final aim. If it is also aim, but that is not the one. What is important is to uncover the material for you. Okay, not covering it. So a topological space X of a Euclidean space X. Okay, so I start with Euclidean space and then I am taking subspace X. Okay, this is called a smooth manifold if at every point X in X there exists neighborhood U of X in X, which is and a diffeomorphism phi from R into U. See, this capital N is something different. This little n is something different. Okay, so this n is also fixed as far as this definition is concerned. And in that case, if this happens, we can put one more thing here, smooth n manifold. Smooth n dimensional manifold, little n here. Inside this capital N. Suppose for each of them you have this phi, right? Okay. The inverse you can write as psi, a collection of u psi, okay, such that the union of all these psi of u will be a subset of x, right? Inside going to x is the whole of x. If that is what it is, such a collection will be called an atlas. Okay. Each such pair u comma psi is called a chart or a local parameterization. So phi is a chart actually. Psi is called a local coordination. So I have mixed it up here slowly. Okay, this must be phi here always here. Okay. Note that C has smooth inverse on psi of u, and these are called local coordinates. Okay, so the local coordinate functions will be from u to Rn. All right, so it follows that the linear subspace, if you take the derivative of the psi, okay, that will be a map from Rn into R capital N, because this u is an open, this u is a subspace of X. The map is from R into R capital N, taking values inside X. So that will be a linear map from little Rn to capital Rn. The image will be a n-dimensional subspace because this is the diffeomorphism. Okay, the derivative has to be non-zero. Okay, so this is some subspace, the linear subspace. It does not depend on the choice of the psi, and is called the tangent space of X at the point of psi X. Okay, its dimension is clearly equal to n, is what I said, because this is a diffeomorphism. That means there is an inverse image. Okay, psi compared to psi is identity. When you take the derivative, composite derivative is identity, derivative of the identity, all that we have seen last time. So this dimension will be equal to n for all the time. What is important is, at the same point, you may have another diffeomorphism, which gives you again the same property. Going inside X, the neighborhood may be smaller, all these things, but the derivative at that point and its image, okay, the full image will be the same. The map itself will be different. Okay, so this is all calculus part. The definition is may not be calculus, but we have taken just the calculus part here. Okay, the union of two coordinate axes, x-axis, y-axis, is not a manifold. So I give you an example of what kind of things are excluded now. Okay, why it is not a manifold? Because look at the origin. At the origin, no matter how small neighborhood you take, that cannot be described by a regular curve. You see, x-axis and y-axis are, each of them is a regular curve, but the union is not a regular curve. At the point 0, 0, 0, 0 is a bad point for the, if you can think of x-axis and y-axis union of curves. They will be curves, okay, in some other definition, namely in algebraic geometry, they are very much important. They are given by just one equation, xy equal to 0. It's also a quadratic equation, right? It's a conic section. Inside the conic section, we have left out one particular case, namely intersecting pair of lines. Intersecting pair of lines is not a manifold. So you may say, whatever definition you are taking, you are leaving out some important case, something important for somebody else. Okay, that is why it is not good to define, make a sacrosanct, rigid definition of a thing, but we can do that restricted to each smaller discipline. Okay, now we are not going to do algebraic geometry, so we will stick to these manifolds for a while. Okay, conic sections in the plane other than intersecting straight lines. Okay, they are all one-dimensional manifolds. Hyperbolas, parabolas, etc. Now, hyperbola cannot be described by one single parameter from any interval. You see, on the other hand, at each point in a small neighborhood, you can do that. In fact, there are two branches. Each branch can be described by a map from entire R to to that branch. So hyperbola is allowed here, right? Which was not the case with our parameterized curve. So we have got something more. We have still haven't got everything. That is the case. Okay, spheres, paraboloids, ellipsoids, etc. are all two-dimensional manifolds inside R3. They are all given by quadratic equations in 3 variables. Okay, if you take all quadratic equations, once again there will be some of them like conic sections, pair of conic sections, and so on. Some of them will have to be, deleted. They will not be manifolds. Okay, but many of them are there in this one. So in this course, you will be studying local geometric properties of two-dimensional manifolds to begin with. And by the time you come to the last week, some global geometries also. Okay, in any case, these two-dimensional manifolds are surfaces. Locally, in a small neighborhood, they are just like they are given by, just like the parameterized curves, there will be some parameterization defined on some open rectangle or an open disk or the whole of R. Okay, so that is the beauty of taking this definition. Whole of Rn I have taken. It includes open interval, open disks also, open rectangles also, and so on, because elementary topology tells you that an open disk is diffeomorphic to the entire of Rn. Okay, so in the definition you can put Rn very safely, but immediately you can see that it need not be the whole of Rn. It can be any open subset of Rn. Especially you can just take open disks, because open disks are whole homeomorphic to whole of Rn. Even diffeomorphic, even open rectangles, open boxes, they are also diffeomorphic to the whole of Rn. Okay, so there is plenty of choice here, but all that choice you need not put in the definition. Okay, so some more examples I give you. If you have a smooth function from U to Rm, where U is an open subset of Rn, then the graph gamma f x comma y belong to U cross Rm such that y equal to fx, that is a graph, right? The graph itself is a manifold. Okay, the function x going to x comma fx itself is a diffeomorphism of U onto the whole of gamma n. So you can restrict U to smaller open subsets if you want later on. Okay, what is the inverse of this one? Take the second projection here from U cross Rm to Rm. X comma y, y equal to fx, right? When you come to y, that will be just fx, right? The first projection, this might be first projection. The first projection is x comma y goes to x. So the composite is the inverse of this one. So this must be the first projection here. There are quite a few typos here, bracket missing and so on. Okay. The problem is I would have liked that a parameterized curve is always a manifold, a one-minded manifold. Alas, that is not the case. Okay. So parameterized regular curve, the image of a smooth map from gamma to A such that gamma dot is never zero throughout J. Okay. Look at the subspace topology in Rn. It may fail to be a one-dimensional manifold. What is the extra thing? We want for each neighborhood of this point T here, the image of the neighborhood must be homeomorphic to the subspace from subspace topology of R on the image. The entire image has a subspace topology, right? The entire image, whatever image you want to take, you want to call it a curve, you are taking subspace topology. In that subspace topology, this gamma may not be a local homeomorphism. Therefore, it cannot be a local diffeomorphism. The calculus is fine, but the topology is, fuzzy. Topology may not be accurate here. Okay, so let me give you a few examples here, which many people make this mistake. They think this one. For example, in your very neatly written book, this point is ignored. Okay, this is a serious point. So let us see what is it. For example, look at this very nice figure 8 curve. You can write down many parameterizations of this one. Okay, one-to-one mapping from an open interval into R2, which will describe this figure 8 curve. Here I have given you one map, you can check. What is happening is the -1 approaches this one like this. Since I have excluded the interval, it is open interval, at -1 this value will be equal to this 0, 0. But I have excluded, that's why I have put an arrow here. It is going all the way. No point is missed, but the end point is already covered by other part, right? So there is no need. Similarly, this part comes like this. It's not covered. Okay. So this is a nice example of when you take a neighborhood of this point, you see just like xy axis, x-axis, y-axis. Similarly, there will be a cross like this. So that will fail to be a manifold, right? But what is the problem with this map? If you take neighborhood of this one, intersect it with the curve, take the inverse image, it will have 3 components. Okay. Whereas only one point here, inverse image of this point is inverse image of 0, 0 is only one point here, t equal to 0. The neighborhood will have one neighborhood around t, but then 2 more open subsets around -1 and +1 will be there. So that is not the topology of the interval. Okay, so that is why the subspace topology does not coincide with -1 +1, the usual topology of R. So this map is not a homeomorphism. There are many interesting examples of this one. This is easy to remember, so I will give this one. Now I will give you another thing which is much more serious problem. Okay. Look at this map, which is e power 2 pi it, comma, e power 2 pi it multiplied by r, some real number. What is this map? It is from R, the entire R, to C cross C. So these are complex numbers, right, of modulus 1. So they are actually taking values in S1 cross S1 contained inside C2. Okay. The only problem here is we have chosen R to be an irrational number. If it's a rational number, this will be a nice curve going along the torus, winding around the torus, and it will be a closed, simple closed curve in the definition of, and it will be a regular simple closed curve, just in the as in the definition of given in the book, and that is the definition we have adopted. It will be a periodic curve if R is rational. if it's irrational, it is non-periodic, it is injective. Okay, what is its image? Its image is some subset, the closure of that subset in the whole of S1 cross S1. In other words, the image is dense in S1 cross S1. Okay. Therefore, what happens? Given any point P in S1 cross S1, every small neighborhood P, okay, every small neighborhood of P will consist of infinitely many connected components, each of which is a regular curve. So in this example, you had inverse image of an open subset consider only 3 components. Here, there will be infinitely many components. And this will happen at every point. So there is no chance of, making any good study of such an object. Okay. Nevertheless, this is a parameterized curve. Whatever we have studied, this is a space curve. All those studies are still valid for this one. So if you want to keep that definition forever, you are welcome, but you are stuck with other things. The moment I go to manifolds, this example will be left out. It is good for us. We don't want to get into this kind of, complicated. The topology becomes very complicated here. Okay. For example, when you are studying Lie groups and so on, you don't want to take this subspace, which is a not closed subspace of C2, right? You would like to have only closed subspace. By the way, this is a subgroup also of S1 crosses. S1 is a subgroup. S1 is a group, right? It's a subgroup of non-zero complex numbers. So S1 cross S1 is a group. In that group structure, this image of lambda will be a subgroup, but it is not a closed subgroup. Okay. So if we just take this one, what is wrong? Something wrong, it is topology that's wrong. So one can remedy the topology by putting an extra topological condition like J is a closed interval. If the moment it's a closed interval, a closed interval is compact. You can use the compactness, right? A closed and bounded subset of Rn is compact. Under a continuous function, the image will be also compact. Not only that, if you have a continuous bijection into Rn, it will be homeomorphism onto the image. So this is the standard topology that you definitely learned in AFS-I. Okay, so that is one way of getting rid of this kind of problems. But as I have told you, if you make only closed intervals, you will have problems with what? You can study real number, real line, or parabola, hyperbola, that kind of lots of other things also. Okay. So an alternative way is to assume some condition on the map, not on the domain. So that is the meaning of that assuming proper. A proper map is nothing but, it is a way of bringing the compactness of J from backdoor. So what is a proper map? Proper map is such that it's a continuous function such that inverse image of a compact set is compact. Okay, so if you don't know that much of topology, let us forget about that. I am not going to use that one, but that is a better hypothesis than assuming J itself is compact. That's all. So for most of the time, what you can do is you may have an entire curve defined all over a non-closed interval. You restrict your study to a closed interval, smaller and smaller, maybe slightly different closed intervals each time. So that way you can bypass this kind of hypothesis. Okay. So now I come to the having got rid of our topological aspects, I come to now the calculus part. Okay. So what happened at a point wherein the derivative is not zero? This not zero was good enough when you are working with one variable calculus. Okay, vector valued function of one variable, also it is good. But now several variables are involved. Map is from U to Rn, where U is an open subset of some Rn, so there are n variables. So this is where the corresponding statement has to be generalized. Okay, it is a generalization of what happens one dimension. It is called inverse function theorem. Okay, so let us study this one carefully, because we are not going to have proof of this one here. Okay, that proof is purely a class, calculus part. So we are going to skip that one. Start with an open subset of Rn. Assume for definiteness 0 belongs to A. Instead of arbitrary point, I am just writing 0 so that I can make slightly easier statements. That's all. Start with a C1 function into again Rn itself. This capital N is here, small n here. Okay, special case. So mapping from Rn to Rn, from E to some Rn. Okay, start with a C1 function such that its derivative at this chosen point is invertible. Not 0 was good enough when you have dimension 1. Now you know this is an n cross n matrix. So non-zero n cross n matrix is not very good. What we want is the whole matrix must be invertible. Okay, the determinant is not 0. Then there exist open neighborhoods of U, open neighborhoods U of 0 in the domain, and V in the codomain F0, such that F, when you restrict from U, it will go into V, and that is a bijection. So statement says that both U and V are open, okay, open neighborhoods of 0 and open neighborhoods of F0. F becomes a bijection. G, if it's a G is F inverse, that is also differentiable. Okay. Moreover, the derivative of G is continuous on the whole of V. In other words, the inverse is also continuously differentiable. Okay. Since we are not looking at the proof here, I want to tell you one thing, namely, suppose I assume this is CR here. Then the proof shows that G will be also CR. Suppose this is C infinity, then the proof shows that G will be also C infinity. Okay. All this happens because determinant function defined on the open set of all matrices which are invertible, that is a smooth function. And it is not 0 there, so its inverse is also a smooth function. Whenever a real valued function is not 0 and smooth, 1 divided by that is also smooth. That is all is involved here. Okay? In the last part. But getting a bijection in a small neighborhood, etc., this is threadbare calculus course. Calculus, it will involve some kind of topology like contraction mapping. Okay. So you can call it analysis because it sounds like the function analysis here. Okay. Now let us set up some more notation. Rn cross Rm to Rn, the first projection I denote by pi 1. Second one I denote it by pi 2. Okay. So x comma y here goes to x, x comma y here goes to y. Okay. Similarly, eta 1 and eta 2 are inclusion maps. Rn to Rn plus m it is the first n coordinates are kept as it is, then you put 0, 0, 0. Here, you put first m zeros and then put v. Okay. So in case of when n and m are 1, 1, r cross r, it is 0, 1. This is x, 0. This is 0, y. So that is the meaning of this. Okay. Easy notations. Don't get confused here. There are no typos here. Given a linear map from this vector space n cross m, okay, here, which is n plus m actually, but I want to think of this as a product, to any other r power r. Okay. So this is a linear map. I can take the restriction of this by composing with eta I. That will be restriction of this first coordinate. Eta I, eta 1. Similarly, eta 2 will be restriction to the second coordinate. Okay, so they are also linear maps. Okay, then you can write the entire A as A1 plus A1 composite pi 1 plus A2 composite pi 2. Okay, so this is similar to writing block matrix and cutting it halfway. Okay, see, you have m plus n times r, or r times m plus n here, r cross m plus n matrix. You can write it as r cross n matrix followed by r cross m matrix. Okay, that is all in matrix terms. That's what it is. Now here is a lemma which is purely a linear algebra map, a linear algebra result. Suppose R itself is n now, the special case. Then I have the first projection here and second projection, right? So first projection is n to n, right? So that is a special case. Suppose R is n, then A1 will be a map from R into Rn, right? Inclusion map followed to into Rn cross Rm, and then to Rn here. So that A1 is invertible. Suppose you assume that. Then for every V inside Rm, there exists a unique U belonging to Rn such that AU equal to 0. So this is a linear algebra map, linear algebra, when a system of linear equations can be solved in a, in terms of a number of variables, fixed variables. Okay, so that is the way you have to interpret this one. So AUV equal to 0, okay, can be solved uniquely belong to Rn, okay, given by the formula U equal to minus A1 inverse A2V. Okay. So I have given you solution also instead of saying there exists solution. It's a unique solution. So this is the formula. You have to just verify this. Okay. So this U satisfies the condition that AUV equal to 0. This is what you have to. Okay. So for every V. So this is a solution. Okay. So this U is a function of V. So this is linear algebra. I told you that calculus was invented to imitate linear algebra, right? So we can imitate that, and what you get is implicit function theorem. This is implicit function theorem for linear maps, implicit function theorem for calculus, general form. Okay, so here the same notations will be used, but the final condition, etc., will be for arbitrary functions which are C1 now, not linear maps. So from linear maps, there's a big generalization. Let E contained inside Rn cross Rm be an open subset. AB is a point of E. F is a C1 function. And capital A is the derivative of F at this point AB. So this is the linear map at one single point. What is the hypothesis? F of AB is 0 and A restricted to Rn cross 0. This is my A1. This is invertible. So I take one single linear map. This capital A is nothing but this DFA at the point AB, DF at the point AB. And the hypothesis on A1 is invertible. So linear algebra hypothesis has come at one single point. Other hypothesis that F is C1 map, continuously differentiable. Then there is an open neighborhood U of AB in Rn cross Rn and a neighborhood W of B in Rm. Okay, you see conclusions are both in the domain and codomain. And a unique map G from C1, unique map G which is C1 map from W to Rn, such that for every point y in W, f of gy, y is 0. So this x here, f of xy equal to 0 is one single solution. Initial value problem. Of course, this is not a differential equation. This is very most general equation than an initial value problem for differential equation. Okay. F of AB is 0, one solution. Around that, you have whole solution here. F of gy, y equal to 0. This g is a function. G of B will be equal to A. Okay, there's a unique map G from C1 to WRN, which satisfies this property. Moreover, the derivative of this little g is nothing but minus A1 inverse A2, where A1 is your A restricted to Rn cross 0 and A2 is A restricted to 0 cross Rm, the notations from the previous lemma. At that point, this map is nothing but the map given here. The derivative is that map. So this is the inverse function theorem. This is the implicit function theorem. Okay, the most general form. Proof is directly from the inverse function theorem. There are direct proofs which prove this one first and then deduce inverse function theorem from this one. So in other words, this statement, okay, and inverse function theorem are equivalent to each other. In fact, once you have proved that one, this comes very easily. By specializing m equal to this Rn cross Rm is there, na? The m equal to 0, the special case. This will give you this one. Okay, but you can get the general form from this one. That is the beauty. Okay, this is a simpler statement, and this complicated statement can prove from that simpler statement. The implicit function theorem proved them. Okay, if you can prove implicit function theorem directly, there are such proofs, then you will get inverse function theorem also. Okay, right now we will be skipping all the proofs. So let us examine a few interesting cases, simple cases here, okay? Going back to one variable is over. You don't get any extra example. There we have already examined. So you have to go to at least two variables, okay, to see some easy example. Take the equation fxy equal to 0 as a system of n equations in n plus m variables. This is n variables x and n variables y. If you are scared, you can take 1, 1, that's all. But notation is the same as if you are doing for two-dimensional case. With AB as a given solution, the theorem tells you under what condition we can solve for the variable y near B in terms of the variable x to obtain a unique continuously differentiable solution. Solution means what? Finally, this gy should satisfy that f of gy comma y is equal to 0. The new function is so obtained is said to be given by the equation f xy equal to 0 implicitly. It's a unique solution in a neighborhood. Therefore, I can give you this time. This equation defines this function. That is why it's called implicit function theorem. Okay, so I will give you an example. X square plus y square minus 1 equal to 0. This is my fxy equal to 0. Okay, function is x square plus y square minus 1. We know already, we are familiar with this one from our 12th standard onwards. Let's define the circle of unit radius and center at 0, 0, right? Observe that we can solve for y uniquely in a small neighborhood of any point AB such that a coordinate is not 0. In particular, take the circle. If the x coordinate is not equal to 0, means either it is in the upper half of plane or lower half plane somewhere. Okay, you can solve for y. At the point 1, 0, you cannot. At the point minus 1, 0, you cannot. Oh, sorry, the other way around. At the point 0, 0, 1 and 0, minus 1, you cannot. That is what it says. Okay. So similarly, the other way around also. Fx of AB is what? The derivative of this. No, this is dfx, I want to say, actually. This is also notation, fx. dfx, df of at AB is twice a. So that is not equal to 0, same thing as a not equal to 0. Okay. So that is the meaning of course, we can do it x square plus y square plus z square minus 1 also 0. So, okay. So solutions will exist. For example, we are familiar with taking y equal to square root of 1 minus x square. But where is it valid? Where is it valid? It is not valid at x equal to plus and minus 1, wherein y will be 0. Right? If y is not 0, you can solve for y in a neighborhood of that point. That is why this is true. This is what. Okay. Now let me give you two more versions of this general form. Okay, one here is surjective form of implicit function theorem. Okay, these will be ready-made to use than the implicit function theorem statement is somewhat more complicated. Okay, so this is like LaTeX as compared to TeX itself. So ready to use things. Let U contained inside Rn plus M, open subset. F is a C1 map into Rn. U is an open subset. Okay, A is inside U. F of A is 0. See, I don't want to write now A comma B and so on. I am not thinking of Rn plus M as a product Rn cross Rn. Okay, the coordinates could be any way, whichever way you like. So this whole thing is Rn. That is why A belongs to U, f of A equal to 0. DFA is surjective. So this is the hypothesis. This is n plus m, and that is n. So this is bigger. That just doesn't mean that it's always surjective. We can assume that it's surjective. That is a possibility. Because anyway, dimension of this one is bigger. Okay, this is a linear map, remember. Then there exists a diffeomorphism phi from V. V is what? V is a neighborhood of 0 inside neighborhood of 0 inside Rn plus M onto a neighborhood of A. V is a neighborhood of 1. So everything is happening now inside Rn plus M. Okay. From 0 to A I am going. I am picking up a neighborhood V of 0. Then phi V will be a neighborhood of Fa. It will be a neighborhood of A. Okay. Phi to phi V. The neighborhood of a neighborhood of 0, V, neighborhood V of 0 into onto this Fv onto a neighborhood 0 of A. Okay. There is a diffeomorphism such that when you compose it with F, let me F composite phi, it will look like a projection to the first n factors. So this is precisely what we did for one variable calculus. The other way around, by the way. So I will come to that one later on. Okay. So this is an easy way of getting the implicit function theorem. See, the elaborate hypothesis there give you automatically DFA is surjective. Because restricted to some coordinate itself, it is an isomorphism. Injective Rn to Rn. Automatically, if you take the whole thing, it will be surjective also. Okay. But which coordinate? You don't know. There it was explicit. The first n coordinates are themselves are such. So we don't know that. So you have to do some linear algebra here in the proof to get this one in the hypothesis of this one. And then apply that and come back. Whereas in application, you don't want to do all that. Immediately you have this one, you want to conclude this one, you can conclude that. So end result is that after diffeomorphism, what is that diffeomorphism? Change of coordinates. First, I am shifting 0 to A. That is one change of coordinate. Then I have to do another change of coordinate at the point 0. Okay. Finally, the function itself in the new coordinates will look like, say, let us say y1, y2, yn plus 1 will go to y1, y2, yn. So that is the meaning of phi of x1, x2, xm, n plus 1 go to x1, x2, xn. Okay. So you change the coordinates here. The first x1, x2, xn plus 1 is a new change of coordinates here. Phi of that were y1, y2, yn. They are the old coordinates. So in other words, the conclusion of theorem is that after a change of coordinates in the domain, we are not touching the codomain at all. The function f coincides with the projection map in a small neighborhood of the origin. Okay. Now come to injective form itself. So you see, the general form contains both of them. So these are extracts. These are like LaTeX commands, okay, as compared to text commands. So what is this statement? Start with an open subset of Rn, okay, 0 inside E. Already I have chosen coordinates inside the domain appropriately. F belongs to C1 of Rn plus M now. The domain dimension, codomain dimension I have interchanged now. Okay. Suppose f of 0 is also 0. So the shifting origin I have taken care here. Okay. Generally, this is not necessary. You can say f of a is b, then you have to shift the coordinates in the domain as well as codomain to make this one. Okay. What is not non-trivial is df is injective now. Then there exists a neighborhood uv, neighborhoods of u, v, etc., 0 and w and so on. Now everything is happening inside the codomain Rn plus m. Okay. So this phi is a diffeomorphism of a small neighborhood of 0 to small neighborhood of 0. Okay. such that after the change of coordinates, the function says that after changing the phi of that, f of phi, f followed by psi, okay, x1 x2 xn is just the inclusion map. x1 x2 xn going to 0 0 0 for all points inside this neighborhood. Okay. So once again, this is repeated for surjective form of implicit function theorem. So I will go to, so actually we can write it as this way, where the r theta coordinates can be chosen like this. At point 0, 1, you will have to do something else. At point 1, 0, you have to do something else. Okay, cos theta, sin theta has to be interchanged. Okay. Here is a little more complicated example. Look at the curve fxy equal to y square minus x cube. I mean, function is this one, curve is y square minus x cube equal to 0. Take this function. I want to take the curve y square minus x cube equal to 0. Can you plot the curve? Have you seen this one before? Hello? No response from anybody? Devi Chandrika? I don't know whether they are actually lasering or not. Satya?
Yes, sir, they are listening.
Huh?
They are listening, but not responding.
They can just log in and sleep off or go away somewhere. You never know. Huh? I'm calling out Dev Chandrika. It's more than half a minute. She is not responding. Kartikeya?
Who is listening to lectures?
Yes, sir.
Okay.
Yes,
Have
sir.
you seen this curve? Y square minus x cube.
Yes, sir.
Equal
So
to
it'll
0.
have like it'll be a reflection of y equals x power 3/2 about the x-axis, but it'll be only defined for the positive x, non-negative x.
Yeah. So the entire curve lies on the left side of the y-axis.
So right side.
Whichever way. Okay. Whichever way. If you want to view it from your side, then it is the right side. Right positive side, let us say. Then there is no confusion. 0, 0 is a bad point. Why? The derivative vanishes at 0. Right? Therefore, implicit function theorem is available at all points A not equal to 0, 0. Right? What is the derivative? This is minus 3x squared, comma 2y. Right? There is a derivative, right? You can write del, the standard calculus notation. Del f is minus 3x squared, comma 2y. It's 0 if and only if xy is 0, 0. Elsewhere it is non-zero. Okay, therefore, at every point other than 0, 0, it will look like a small arc. That is the meaning of this theorem. Okay. It has now no conclusion. It doesn't say anything about what is happening at 0. Okay. Indeed, at 0, you cannot have a smooth curve to describe that part. Cannot. Okay. One parameterization of this one will be what? T square TQ. But there may be other parameterizations. But no parameterization will give you this curve around the 0, 0, and which will be regular. Okay. So that is not involved here. That the implicit function theorem doesn't say that. All right. Actually, it says that because the function is this one. This is given. Parameterizations are not given. Okay. So if you can solve it, then this curve should have been a regular curve at that point. So in some way it is 1, 1. I mean, it is if and only if part. Okay. Okay. So inverse function theorem says that is a neighborhood like this here, such that xy is equal to psi of phi of vxy equal g of this one, blah blah blah. So finally, when you can phi composite this f, projection to the first factor will be x. The inverse may not be unique. And that is not a statement here. All right. Do you want any more explanation here? I think I can stop here because it's already time. So next time we will apply this theorem, especially this last one, the implicit function theorem for injective form. Okay. There will be some applications of this one. We will have application for curves also. Okay. And this will be used heavily from your second part and third part, and later on finally in the last part also. Okay. Just like our definition for curves, you can give a surface patch, parameterized surfaces. Okay. They will be dangerous. They will have the same problem like what we have indicated with this figure 8 and so on. Okay. But if you restrict it to some closed rectangle or a closed disk and so on, they will be fine. So you have to be careful with the definition of the kind of parameterized neighborhoods and so on. Okay. Around each point in a small neighborhood, we can do something, but don't confuse it with the topology of the image. That's all. Any questions?
I'm stop recording, sir. I'm stopping the recording.